So then we get to guidelines for using the regression equation for predictions. This is kind of the money portion of this chapter. The main reason we do regression analysis is to make predictions. The main reason we do correlation analysis is to tell us if we can make predictions. We'll talk about that here shortly when we write out our guidelines. And so this maybe doesn't get enough fanfare as it should in the notes, but this is why we're here. Now we have to do all the other things. And so just because it's why we're here doesn't mean it's the only thing you're going to be tested on. But this is the crescendo of why we're doing everything in this chapter is to get to this point. But we have to know, can we make a prediction? Okay, so we'll do this in our examples. We will make predictions. We will say, here's the equation. Here's what would my y be given this x? And it's simple. We just plug in to make a prediction. If I think x is 5, go to the regression equation, plug in 5 for x and see what y hat is. And now I've got a predicted value of y. But we have to note these 3 guidelines. If these 3 things don't hold, then I don't want to make a prediction. And so why did we spend all of that time previously in that last video talking about correlation? Well, it's for this. We can only use the regression equation for predictions if the graph of the regression line fits the points reasonably well. This is the eye test. We talked about this last video. If I look at my scatter plot and I'm drawing a line and the points don't fit the line very well, if I just look at it and I say, I don't think there's really a great relationship there, then I don't want to use the regression equation for prediction. I need to make sure that by looking at the picture that the line fits the points pretty well, then I'm allowed to make predictions. Number 2, only use the regression equation for prediction if R indicates there is a linear correlation present. Again, why did we spend the time last chapter talking about R? We need to make sure that R is sufficiently large. Now, notice I'm not giving you a threshold here. I'm not saying R has to be above a certain number. Remember we said R is not very robust. Okay, what that means is an outlier can really affect the value of R. So I want to make sure R is reasonably large, but there is no cutoff for it's large enough or it's not large enough. It's partially, I also need to look at the above point. What does the picture look like? It's a judgment call where we say if R looks okay and the picture looks okay, I'm good to go. But if one of those is really wonky or neither one of them looks very good, then I would not use the regression equation for prediction. And the last one is use the regression equation for predictions only if the data do not go much beyond the scope of the available sample data. If you try to make a prediction beyond the scope of data you have, that is called extrapolation. We do not want to extrapolate. Why is that? It's the idea that if I have data over a certain range of x's and I try to predict for an x outside of that range, I don't know if the same trends holding within that range of x's is going to hold outside of that range of x's. Maybe it is, maybe it isn't. Predicting outside of that range is called extrapolation. It's generally a bad thing. It's not always a bad thing, but generally a bad thing. And so for our purposes, we're going to say we're not going to want to do that. The exception to that rule is going to be if you're an expert or you talk to an expert in that field that says this is safe to do. Okay, that's the only reason that we're going to be allowed to extrapolate is some expert tells you it's okay to do so. For this course, since none of us are experts in the same thing, we're not going to extrapolate because I cannot assume that all of you are experts in the same things and you would have this expert knowledge. So for our purposes, we're going to say there's no expert telling us we can extrapolate. We only want to make a prediction if we're predicting within the realm of the scope of data we have. Now, that doesn't mean that if my x's go from 2 to 12, I can make a prediction for 13. That's okay. I can't make a prediction for 20. Okay, if my x's go from 100 to 200, I can make a prediction for 95. I can't make a prediction for 25. Okay, I need to be either within the range of data that I have or really close to it in order to make a prediction. And you might be saying, why is that a bad thing? How about this? How about if I put a scatter plot together and my x-axis was age and my y-axis was height and my data was compiled on children, specifically children we'll say below the age of 15. That would lead to a relatively strong positive linear correlation. No one grows perfectly linear, but again, if I'm plotting heights of a bunch of people, in general, I will have an upward trend. And it won't be an R of 1, right? But it'll be an R of 0.7, 0.8. Because as people get older, they get taller. Okay. If my data then only exists between the ages of 0 and 15, notice what would happen if I tried to make a prediction on someone's height at age 50. I'd predict they're 15 foot tall, right? We know that once uh, humans get past a certain age, for females, probably more in the 17, 18 range, for males, maybe 18, 19, 20, right? They tend to stop growing, right? Most humans of either gender don't tend to grow past really 21, 22. And even then at 21, it's still kind of rare. And height flattens off. But if I were to predict the height of someone age 50 based off of children's data, then I would predict very erroneously. And why is that? Because the trend that happens within my data from 0 to 15 age range doesn't happen beyond that. And you say, well, obviously, I'm not going to do that. I'm not going to predict the height of a 50-year-old based off of children's data. Okay, but that's the point, is that you know not to do that because you have a good understanding of what heights do. When you see a new data set, it goes back to unless you're an expert in that area, you probably won't know what's going to happen beyond that data. So we always want to err on the side of caution of saying this might be like height and age. It might be a situation where I see the trend here in my data range, but I don't know if the trend goes beyond that. If you want to make a prediction, then you need to get data for where you're trying to predict, right? If my X's go from 0 to 100 and I want to make a prediction for 25, let's start getting some data around 30 and 40, right? I just want to make sure that I'm predicting around where I have data. And if I know I want to make a prediction, I want to get data around where I want to make a prediction, okay? Because this can lead to some really erroneous conclusions. Now, there's no place for this in your notes, so you may want to make a note to yourself here. What do you do when you cannot use the regression equation for prediction? Well, this is where I want us to stop, take a deep breath, get out of math brain, and just use some common sense. If I have a bunch of y values and a bunch of x values, and I'm trying to make a prediction on y, and I have a regression equation, that regression equation gives me a better prediction from y because I know what the x's are, if I assume the x's and y's are related. But if the x's and y's are not related, if they're independent, and I want to make a y prediction, how would I have made a prediction on y back in previous chapters of this course? What I would have said previously was, if I want to make a prediction of something, I want to make the best guess at something. That would be the point estimate. And if I was guessing and I wanted to make my best guess at any value, I would just take the average of the data set, right? And so the idea is that if I have a data set and I want to make a guess as to what the next observation is going to be, just take the average. The benefit to the regression equation is I can do better than the average. If I have x and y related, if x and y are related and I know what x is, I can make a better guess. I can make a more informed guess. Think about the height example I just talked about. If I wanted to know what the height of a kid was, I would just take the average height of kids, right? If I didn't know anything about, if I didn't have x values, ignoring what we just talked about in this chapter, if I just wanted to know what the if someone said there's going to be a kid that walks into the door and I need you to predict how tall he is, I would just say, well, what's the average height of all kids, right? And then, the 3'6", we'll say, I don't know. And that'd be my best guess, right? But if I know more information that's related to height, like say age, like now you told me, it's not just that you're telling me it's a kid that walks in the door, but a kid who is age 12, I can make a better guess now. And that's when you plug into a regression equation and you say, because I know that 12-year-olds are going to be a little bit taller, plug it into the equation, and it might give me a height of, 4'5" or something like that, right? So it's this idea that when I make predictions, this isn't any different than what we've covered before. Before, a prediction would have just been the average, right? Because we said x bar is the best point estimate for mu. And so the same thing here, that y bar would be the best prediction for y. right? The average is always my best guess in lieu of anything else. It's just that if I have a regression equation and I have these two variables that are related and I'm not extrapolating, that's going to be a better prediction. But if I can't make a prediction here, don't forget all the things we talked about before, because you already previously learned how to make predictions and what our best guess as to some value would be. And then we have one last concept here to talk on, and that is the concept of explained variation. Explained variation is the proportion of variability in the response variable that is explained by the relationship between x and y. The idea behind explained variation is, think about a pie chart, and that pie chart is y, why, the value of y, the letter y, is what it is. Why are you the height you are? Why do you have the GPA you have? It could be any response variable y that we can talk about. And explained variation is a pie chart of why that is what it is. And then we can divvy up that pie chart. Just thinking from common sense, I can divvy up that pie chart into all of the reasons that y is what it is. So in the example of height, why are you the height you are? For just some of that variability is explained by your father's height. Some of that variability is explained by your mother's height. Some of that variability is explained by random chance and variability, just randomness. Okay, let's talk about your GPA. Part of why you have the GPA you have would be how much you study. Part of it might be the background and training that you had in your grade school days. Part of it might be, do you have to work a part-time job? Right? That'd be part of it, because if you're having to work, or a full-time job, right? If you're having to work a job, that probably is going to affect your GPA a little bit. If you're not having to work a job, you have more time to study. Part of it might be how much sleep you get. Part of it might be if you're eating a healthy diet. Part of it, I mean, there's dozens and dozens of reasons that we can talk about as to why your GPA what it is. Explained variation is basically just saying how much of the response variable can be explained by this equation that we've modeled. And when we say explained variability, what we mean is you have a certain GPA and your classmates have certain GPAs, and people that you see in the hall have certain GPAs. Why is your GPA different than theirs? Well, part of the reason is, again, study habits or sleep or background or the classes you took or your major or who knows what, age, anything, right? So it's saying there's variability in these Ys. Some Ys are bigger than other Ys, right? Why, again, or height. Why are you taller or shorter than the last person that you saw? Or the person that you're going to see next? Well, because of this and this and this. Okay, maybe a little bit diet, maybe a little bit random chance, maybe a little bit, who knows how much sun you got as a kid. I don't know. That probably doesn't make sense, but right, it's this idea of we can come up with all of the different reasons why in WHY the different Ys, the letter Ys, are what they are, and some are higher and some are lower, and that's variability. And so how can I explain that variability? That's what explained variation is just what percentage of the response variable is explained by this model that we've come up with. And we specifically do that via the coefficient of determination, which is denoted by r squared. This is similar to r that we talked about in the last set of videos. Why this r is capitalized and that r is lowercase is irrelevant. You can capitalize in both or lowercase in both. It's not a big deal. This is the square of that r. So if you have one, you should be able to get to the other one. And it's just like that in that one with regards to the fact that correlation could be measured in a lot of different ways, but we tend to do it with the letter R and that specific version of it. Explained variation can be measured in different ways, but we're going to tend to do it with coefficient of determination, which is R squared. And that's your first note, that it's not the only way to measure, but it's the most common. So again, parallels just like we saw before. Because r squared is the square of r, it has to be between 0 and 1 right? Because a negative times a negative is a positive, and any number between 0 and 1 squared stays between 0 and 1. And the last note is that a coefficient of determination of 0 or 1 indicates that the least squares regression line explains none or all of the variation in the response variable. So if r squared is 0, it means that you have explained nothing. It might be my example of why people are the height they are, how much sun they got as a kid. It explains nothing. We could build a model and our r squared would be 0. You'd say you got all this data and you explained nothing. You go the other direction and r squared of 1 indicates that we've captured everything. Everything of exactly why, I could tell you exactly why the response variable is what it is, and it's because of what we've captured in our model and the data we've captured. Okay, notice what we're going to do here is R is always written as a decimal. When you square it, then to get R squared, you are still between 0 and 1. Sometimes, not always, that will be reported as a percentage. You just kind of go with it. It could be a decimal percent, no big deal. It's commonly written both ways.